Okay, so now that you've seen how we can use the concentrations of the reactants and their exponents and the value of the rate constant to figure out rate, what we want to be able to do next is use the rate and the concentrations of the reactions to figure out the exponents. It's a little bit trickier, but not too tricky. We're going to start with an example. What is the rate law for the reaction A plus B goes to C given all this data? So this reaction was run 5 times. And the first trial, the concentration of A was 0.1 and the concentration of B was 0.5, and they were mixed together, and the rate was found to be 0.053. And then they did it again. The concentration of A was 0.2 and the concentration of B was 0.3. And they mixed them together and they found the rate was 0.127. And they did it a third time with different concentrations, and a fourth time, and a fifth time. And they got all this data together, and they said, let's use this data to figure out the rate law. The generic form of the rate law for this reaction is rate equals the rate constant K times A to the X times B to the Y. In order for us to solve the rate law or figure out the rate law, we need to determine the values of X and Y. So what we're going to do is pick a set of data. I'm just going to choose one of these 5 sets of data, and we're going to take the value of the rate and the concentration of A and the concentration of B, and we're going to plug it into our starting point for the rate law. I'm just going to choose data set number 2. Ignore the crossed off stuff for now. And so I'm going to say with data set number 2, the value of the rate was 0.127. And that's equal to the rate constant K, I have no idea what it is, times the concentration of A in data set number 2, that was 0.2, raised to the X, don't know what X is, that's what we're trying to figure out, and then that is times the concentration of B for data set number 2, it's 0.3 raised to the Y. And again, I just chose to work with data set number 2. You could have chosen to work with pretty much any 5 of these sets of data. Actually, data set number 1 is a bunch of garbage, but we'll talk about why that is in a little bit. You could have chosen to start with any set of data and write this stuff down. It doesn't matter where you start. Now, in this equation, we have 3 unknown variables, K and X and Y. We're trying to figure out what X and Y are. We can only solve for one variable at a time, or at least I can. I don't know if math lets you solve for 3 variables at once. I'm not, I don't think so, but I didn't go to the top in math, so maybe there's something I didn't learn. But as far as I know, you can only solve for one variable at a time. So we're going to need to choose one of these 3 variables to solve first, and I'm going to choose to solve X first. So what I'm going to do is go back to my set of data, and I'm going to choose a second set of data that I'm going to also do the same thing to, fill into the rate law. That second set of data is going to allow me to beautifully cancel out 2 of the 3 variables, unknown variables in this equation. The other set of data that I'm going to choose to work with is data set number 5. And so underneath data set number 2, I'm going to write the rate law again, plugging in the values from data set number 5. So I'm going to say the rate is 0.509, and that's times K, which I still don't know what it is. The value of A is 0.4 raised to the X. The value of B is 0.3 raised to the Y. Now you see, if I do this like a big division problem, I don't know what the value of K is, but I know that it's a constant. So K divided by K is 1, and that whole term just drops out, cancels itself out. I also don't know what Y is, but I know that Y is a constant. So 0.3 to the Y divided by 0.3 to the Y is going to be 1, and that drops out of the equation as well, which lets me simplify my equation down to this. 0.127 over 0.509 is equal to 0.2 over 0.4 raised to the X. So when I chose the second set of data to use in this equation, I carefully selected a set of data that had the exact same value for the concentration of B, because I knew that that would allow me to drop this whole term right out of the equation. Okay, so if we do our math to solve for x, we do our algebra, solve for the left side of the equation, it's 0.25. 0.2 divided by 0.4 is 0.5 to the x. You do your math and you get a value of 2 for exponent x. So we've got one of our exponents solved. Now we're going to move on to solving exponent y. And we're going to use the same kind of strategy as we used here. So we're going to choose two sets of data from the 5. And this time we're going to choose two sets of data where the concentration of A is being held constant. So we could choose either data sets 2 and 4 because those both have 0.2 as the value of A. Or we could choose data sets 3 and 5 because they have both 0.4 as the value of A. We're going to choose data sets 2 and 4. And so we're just, again, going to plug these values in from the data sets to the rate law. Data set number 2 had a rate of 0.127 equals K times the concentration of A, 0.2 raised to the X, times the concentration of B, 0.3 raised to the Y. And data set 4 had a rate of 0.254. That's equal to the rate constant K times the concentration of A, 0.2 raised to the X, times the concentration of B, 0.6 raised to the Y. K cancels, 0.2 to the X cancels, and that leaves us with 0.127 over 0.254 equal to 0.30 divided by 0.6 raised to the Y. And again, we use our algebra to solve for the value of Y, and we find that it's 1. You could, of course, actually, no, you couldn't. I was going to say you could, since you know the value of 2, you could just kind of skip this and plug 2 in for x and solve for y, but you actually can't because you have that unknown value of k. So you have to use this strategy both times. Once we have our exponents figured out, we just rewrite the rate law using the actual values of the exponents instead of writing x and y. So we found that the value for x was 2. We plug that into our new rate law, and the value of y is 1, and we plug that in. And our rate law is now rate equals K times A to the 2 times the concentration of B. We never in the rate law give numerical values to the rate or to K or to the concentrations of the reactants. Part of that is because these things can change. The rate changes, as you can see from the data. The rate changes and as the concentrations of A and B change. So these are things that can be modified in the reaction. It doesn't change the rate law. The rate constant K also does change with temperature, and so I think that's why it's left out of the rate law too. The order of the reaction does not change. That's something that always stays the same regardless of concentrations or temperatures. So this reaction overall is a third order reaction. 2 plus 1 is 3. It's second order with respect to A. It's first order with respect to B. And that is the end of section 13.2.